you have any issues, we can work around that, but just want to check. So what we're going to do here, how many of you are already registered to use UC3? Yes and no, not for the purpose of this question. So what we're going to do is walk through a registration process for logging into UC3 Sub and look at how to do job submissions. And the same kind of submissions you do on Tier 3, you can also do directly on UC3 Sub. And so what we're going to do is look at some very simple examples of how to do that. So the first step is to go get signed up. Now, I'd like for those of you who are already signed up to just play along as if you're not. The reason for that is we have a new registration system and we want to collect a little bit more information and make sure that we have current information about you, how to reach you, and what your engagement is with the platform right now. So if you go to uc3.uchicago.edu here, there's a link up at the top for register. I'd like everyone to click on that, even if you're already registered, just to walk through that process, and then log in with your CNET credentials. We'll get a page somewhat like this. Yours will be a little bit different. You won't have all the things. Otherwise, this should be pretty much the same. So I'd like everyone just to make sure that this information is up to date for you. Make sure that we get your current email address and phone number, your project affiliations. If you need to take a little bit, we're going to kind of move quickly here, but if you need to take a little bit more time to do that, whenever you can do this is great. The reason we're collecting this information is because this project board is a site that gives us the capability to associate individual users to projects and keep track of what we're doing with those projects so that we know on an ongoing basis what we have done for you, what problems you've brought to us, and we can make sure that we are continuously meeting your needs accurately. Going through this registration process will help us achieve that. If you have already, or I'm sorry, if you've not registered already, then going through this step is going to open a ticket with us to get you enabled. Sometimes that can take a little bit of time because it's a manual process, but today, we're all sitting here and we're going to get you registered right away. So as soon as we get through this, everybody will be able to log into the UC3 ad and begin submitting jobs. Anyone having any trouble with this? Is it, get it up okay? And okay. I want to make sure that, because our next step is going to be to log into the cluster and actually start doing these tutorials. I just want to make sure that we've got that running along. So one comment here for the project affiliations, at a later point, we will be associating you to projects in this project board. So if you can just let us know what projects you're working on, we'll figure out how to integrate that with the project listing after the workshop today. So I'm going to go back to, actually I don't need that right now. Open up the tutorial. Should I wait a little bit for anybody, or are we all okay? Okay. So next thing we're going to do, you need to open up an SSH session. I'm going to open the tutorial document here, and we'll start walking through it. And the first step here is to log into the UC3 environment. We do this with SSH. If you have an SSH client on your machine that you're comfortable using, that's great. If you do not, we actually have an SSH client on the UC3 website as well that you can use up here in the corner with Web Connect. You can click on that and it'll give you a little SSH window. So if you lack an SSH client at any time and you need to get into the cluster, that's a way to do it. Not necessarily the best way, but it's usually available when other things are not. So when you log into the UC3 environment, you should see a screen kind of like this, the message of the day with your login prompt. And we're going to be doing the demos today as the CNET ID user. So what you will see in the demo output on this screen will have the username CNET ID. As you're doing these along with us, you'll see your user ID there in place of CNET ID. So the first thing to do is to set up the tutorial. We've actually pre-typed the entire tutorial for you so that we don't need to sit here and everyone tap away to put in the submit files and everything. And to get that going, we want to run the tutorial command. So do that, tutorial quick start, and it'll give you a little bit of introductory text. Shows up okay. About what this module of the session is going to do and how to get started. So you just run that. It creates a tutorial directory for you, and we'll be in there. So there are a few files here. We're going to go through 4 different job submissions. Each one of those has a subfile associated with it, and each one of those is going to use a program, a job named short.sh, which is kind of a little do-nothing job, but it's going to illustrate our points. So the first thing to do whenever you have new work to do in the cluster is to figure out what your workload is. Sometimes it's useful to set up a wrapper script to do that. Sometimes you can just run directly whatever application you need. But it's a good habit, I guess, or a good skill to have to write these wrapper scripts, and that's what short.sh. The big workload that we're doing here is to just run going to sleep at the end for a certain amount of time so that we can control how long the job executes and get a look at the parallelism of launching multiple jobs and so on. So the short.sh job, we have a new directory. We're going to control how this runs through the submit file as we move along. The first thing to do anytime you create a new workload is to run the job locally. UC3 sub is available for that, and it's really important before you start submitting a job at large scale onto our seeder or onto remote clusters or anything like that to make sure that your job is going to do what you expect. If it ends up tying up a lot of CPU time and doesn't get you what you need, then people can notice that. So we want to make sure that to the best of your ability, it's doing, Sam's smiling. We want to make sure that to the best of your ability to figure that out, this job is doing what you want. So usually you set up the script, you run it locally, tweak it until you have it doing what you expect, and then move ahead. So if you run this job on your terminal right now, you should see some output sort of much like this. Different username, different IP address maybe, but pretty much like this. And this job can't go wrong. So right now we don't need to worry about whether it's doing anything wrong, but as you develop your own workloads, analyze that and make sure that you're getting the results you want. The next step is to create a submission file. And the submit file is a set of parameters to instruct Condor on what needs to run, how it needs to run, how many times you want it to run, what attributes you need on the worker nodes that it ends up running on, various things like this. So this is a minimal submit file, this tutorial 01, pretty much the least that you can get away with. What we do first is define the universe. This is the class of machines that, sort of a combination of the class of machines that your job will run on and how it will be pushed to those machines. There are other universes for doing things like virtual machine launches and stuff like that, but we don't mess with those. Pretty much anything we do here on UC3 can run under the vanilla universe. Then you define your executable, which is just our short.sh file. This is relative to the directory that your submit file is in, or the directory that you submit from. Usually just do everything within one directory. Ideally both, but really it's the directory you submit from. Right? So Condor is going to pick up the environment from where you are, but really, in general, you want to have your submit file and all of your work materials in one directory, and have that as one discrete object get moved around, because to some extent, Condor needs to replicate your runtime environment to every worker node. So it's best that you just have that level. So this is relative to the directory you're in, which is the UC3 quick start folder. Then we define where the error and the output of the job are going to go. In a Unix environment, you have the standard error and the standard output. And this puts the output for each of your workload into a different file so that you can analyze the results of those jobs independently. And then there's the log parameter is an overall log for the submission of the job. We won't get into it in detail. Tutorial job equals true is a parameter that we have today, but that you're not generally going to use. It ensures that some cores are available for your job today during the tutorial. A counting group is something that you do need to use as you're putting jobs into UC3, because this helps to assign your utilization to a group so that we can understand who's using the facility and get accurate graphing of where the resources are being delivered. And then finally, the queue line tells how many instances of this job you want to run through the submission. In your directory, this file is much more commented. You see it right there, lots of comments to explain what each of these parameters is. But through this tutorial, what we're going to see on the screen is just the abbreviated version. Every time we look at a tutorial, a submit file on the screen, we're going to have the abbreviated version on the screen, but you can click to see the fully expanded version that's in your directory. So the next step is to submit this job. So use the condor_submit program to do that. The argument is the submit file that you want to run, and it tells you I'm launching a job and gives you a cluster ID for it. A cluster ID is just an identifier that refers to however many jobs you submitted from this submit file. Later on, we'll see how to do more than just one, but right now you have a cluster ID that represents a single job. Take note of that. We're going to use it for monitoring the status of the job with several commands, but first of all, condor queue. This tells you what is the status of your job, and if you run it right away after you submit, you can see the status of your job as it's shown here. If you wait too long, your job will complete and will no longer be available in condor queue. Has everyone seen this, or has the job already finished, or any questions about it? So you can get status on a specific job cluster or on everything that you've got. Condor queue with no arguments will show all jobs on the scheduler. Condor queue with your login ID, your CNET ID, will show all of your jobs. And then with a numeric argument, it'll show jobs under that cluster ID. So if you give it the cluster ID you just created, you'll see only that job. And later on, we'll see it showing more jobs. Once the job is done, you can see largely the same information using the condor history command. This queries the history of the submit environment and looks at all the jobs that have run. And with pretty much the same syntax, you can see the same information queried from the job log rather than from the current scheduled processes. So if you run job history, I've been talking too much to do the condor queue, but we can do a condor history right here. Actually, we need to do a submit. Got 87416. I can still see that in the queue. Now it's running. You see right here the status has changed from I for idle to R for running. Now if I run it again, still running. It's got 12 seconds on it, and it's sleeping for 15, so it should be done pretty soon. There's a little bit of overhead to running it, so it usually takes a little bit longer than you expect. Now it's gone. So if I do a condor history, now I see it in the completed state, C for complete. And that takes a little bit longer to run because it's querying the full job history in the submit platform, but it shows you much the same information. So that'll tell you what the status is of all the, you submit 100 jobs, walk away for coffee, it takes them an hour and a half to run, whatever, you come back and you can see what happened to them, even though you haven't been sitting here monitoring it with a hawk eye. So once your job is completed, you can look at the output using those error and output files that we defined in the submit file. If I look in the log directory now, I've got job.error and job.out. There should be no error for this job because it's a cannot fail job. That's an empty file. And if I look at the output, you see much the same thing as what you saw when you ran that interactively on UC3 sub, and generally you should expect that. You will notice, though, that the environment now contains a lot of Condor parameters, and these are values that Condor uses internally to manage the execution of the job. Sometimes those can be useful for debugging why your job went wrong, but we're not going to go into details on that today. It's just useful to know that they're in there in the environment. If you need to debug a job, you can have your job print the environment and see what's going on with that. So moving on, we can ramp this up.
We pause right there. So we just finished job one?
We just finished job one.
Okay. Everybody got through job one then?
Okay. So moving on, we're going to submit 10 jobs now. Tutorial 02.sub is the same submit file as tutorial 01, but we have modified the queue line to submit 10 jobs instead of just one. And when we submit that here, we're going to see a slightly different output. There are now 10 periods after submitting jobs. Condor submit shows you 1 period for each instance of the job that you run. So we're going to run a Condor submit here. Now I have cluster 87420, and if I run Condor Q 87420, I will see my 10 jobs sitting in idle state waiting to be scheduled. Mm-hmm.
So there a way to just
You can do that, but it sort of depends on the details of how you set up your submit file.
It's kind of like a manual process. There are tools that are called sweep, but there are other documents. Then some fail, you retry them. So Condor has a tool we just Condor submit.
Eggman is a manager using directed acyclic graphs to chart dependencies between jobs. So that's why it has this capability, because it can see the relationships between jobs that finished and did not. So we're going to look now at a couple of, did that cover your question, Sam?
Yeah.
Okay.
No.
Yeah, it's kind of a more advanced topic than what we're looking at right now, so we can certainly talk to you more about it
We have a
afterwards.
sample tutorial. And Sam already uses it. Yeah, the jobs still fail. I was wondering if there's like a manual way. Yeah, and then I resubmit that. So I do that 3 times. I know it's like if you want to do it manually.
So these jobs have finished. I'm going to submit this job one more time to show an approach to monitoring the status of the job. So we're going to get this new cluster ID is 87428. And there's a handy command called watch that will allow you to run the same program again and again and refresh the screen every time it runs it. So you can sort of see in a little ASCII animation what the progress is of your jobs in the queue. This is really nice to see, are my jobs completing? If you can expect in real time to see your jobs finishing, very often that's not the case, but maybe you want to leave this running and just monitor what the status of all your jobs is. you can do that. You see 6 jobs just disappeared. They completed, and 4 more got scheduled and are now running. So this is a handy tool for keeping track of what the run state of current jobs is. The other way that you can wait for jobs to finish is to do condor wait log job.a7 428 job.log. Here's the control key. Okay, so if you do a condor wait command, this returned right away because all the jobs had already finished. But if there were still some running, condor wait would just sit there and not give you a prompt back until all the jobs are finished. So this can be kind of useful as sort of a poor man's DAGman to stage another step after your job's complete. And then looking at the history, you'll see that all these jobs have completed with the status C as well. So we'll call that good for tutorial 2. Any questions about that? Right, sorry, press Control C. That's the way to get out of watch. I wish that you could just press Q or something, but yeah, Control C will get you out of watch. Okay, so tutorial 3 for this phase is to, or job 3 is to add an argument to your executable. Sometimes you have a job there where everything you need is in the script. You don't need any control from outside. Other times you want to vary the arguments to your job. If you have a wrapper where pretty much the entire nature of your job is encapsulated in this shell script, but the specifics of how the job runs can be passed in on the command line, then arguments gives you a way to do that. So in tutorial 3, we change a couple of things. First of all, we're adding this arguments line here. Adding the number 5 to the short.sh file. If we go back and look at what that script looks like, it takes its first argument as the amount of time to sleep. So this is absolutely just a property of this job file, or this shell script. Your script is going to be different, and whatever arguments your script needs can be passed in here using the arguments parameter. Everything up to the comment, yeah. The comment too. Okay, the comment goes too, but since it's a comment, it doesn't do anything.
Condor submit file takes everything up to the
And that's true for pretty much everything in the submit file, right? Lines with a backslash. So this job is going to run with an argument of 5. It will sleep for 5 seconds, and we are going to ramp it up to now 100 instances of the job. So we're sleeping less time so that we don't have as much hit on the scheduler during the tutorial. And we'll run tutorial 3 now under condor submit. You're going to see 100 dots as this submits. Your job submitted to 87451. Your job cluster ID will be very close to this, but different. And we'll do another condor watch. Here, with this watch command, I'm doing my username, so I don't need to keep track of the job ID or the cluster ID for this. I'm just watching all my jobs, and I know that the only jobs I have live in the system right now are associated with this. So yeah, there you go, Marco, you're right. The comment is in the command.
I mean, if someone's following along literally here, you hit CNET ID, you're seeing David's.
Right, you're seeing my jobs.
But if you want to use your own CNET ID.
Good point. So we see now a lot of jobs have finished. They're all done. So Is everyone else's done too, or have we kind of gotten a lot of things into the system? Great, we must have a lot of cores available. So we're not going to do the Condor wait because we just sat here and watched it. There's some more text in here if you want to read through this. But right here, we have a little bit of information about how you can analyze the results of that run and see how well it ran, how much time it went through and everything. This can be maybe a useful tutorial to go look over again later, but we're going to skip over some of this stuff for now. All of these little emboldened bits of text here with the arrow next to it are things you can click for some more information that we don't really want to look at in too much detail. So let's look at, we've submitted 100 jobs. Those probably got pushed around to quite a number of different places. We only have whatever small number of cores on the submit node. So they're not all going to run on the submit node. They're going to go out to a variety of places. If we have 10 people here running it, then we just run 1,000 jobs. They have to go somewhere. So let's look at where they went. The Condor history-long command will give you a wealth of information about how your job ran, what it was doing, how many resources it consumed, what kinds of requirements you set up for it, and all kinds of things like that. The thing that we're most interested in right now is what host it ran on. And if you look at the full output of this, you can sort of scroll through there and see what is the parameter that contains a host name. That is going to be last remote host. So we can do this command in the terminal, but I'm going to do it with my actual job ID that I just created, 87428. This is going to show me all of the slot names. It's not just the host name, but all of the slot names that that this ran under. 87451 is the right job ID, cluster ID. So yeah, 100 lines here for each slot and each host name that my job went to. That's a lot of information to process. So there's a technique we have here to reduce that set of information to individual hosts. And it uses the cut command to slice out the host name that it was running under. And then a handy command called distribution that plots a little distribution curve in your terminal window. This is going to show us what the distribution was of the hosts that this job ran on. So we see eight of my jobs ran on UC3 sub, 5 of them ran on C009, and so on. Obviously, sub took a large portion of the hit here. Did anyone running this, do you see significantly different host names over there? Anything different from UC3? Generally, the host name will tell you something about what cluster it's running on. So if I got a host name over there with UC3, then this would be, I'd be borrowing SAM's resources from the tier 3. It could be running on some machine at, I don't know, at UW, and then we'd know that it was flocking out to OSG and so on. So this is useful for knowing what kinds of resources you're receiving through UC3 and where you're hitting. Mm-hmm. So you're like generating a submit file Q1, Q1, Q1.
So like instead of what would be awesome, but can actually
You can do it for user Meehan, but then you're going to get all the jobs you've ever run. Right.
What you can do is you can put host name
Right. So let's take a look at that. In the log directory here, I have now 111 files for output, for error, and then like four log files. Let's look at one of the job.out files again, 87428-1. So because I set up the short.sh file this way, it is running, or it's showing the hostname that it ran on in this output. Job is running on node UC3 sub. So if you make this a part of your job wrapper as a standard routine, then instead of looking at Condor history for that information, you can grep it out of your log file as well, or your output files. That's what Lincoln is saying. And then pipe that into distribution. Distribution is a fairly smart program. If you hand it a lot of single keys, it'll do the simple sorting and uniquing on that input. And you can also give it key value pairs if you want to get it a little bit more advanced. Okay. So that covers our example 3. The text here shows that at times your jobs may flock out to more than one cluster, and this trick here with distribution, like I was describing, will show you what clusters those ran on. This command here, which we don't need to run, is a technique for isolating the cluster name from the host name that works for many clusters, but not all. And you can use that to find out, well, so in this example, 57% of my jobs ran on the UC3 Cedar, and 43% walked over to the UC Tier 3 Atlas. If you have a lot heavier weight jobs than this, you may see some more interesting results there. So any questions about this before we go to number 4? Okay. So the last thing, and this is going to be pretty quick, is just a brief introduction to job requirements. UC3 is not a cluster itself. It's a means of aggregating cooperative computational resources. So these each have different constraints. They have different uptimes. They have different business cycles. Sometimes they're busy all day long and free during the night. Maybe they're, it depends on the cluster, you know. They have different, you know, we don't do a lot of work during the summer. So during the summer, this site is highly available. But during the year, it's not. So each of these resources may have different attributes. Also, they may have different physical attributes. A lot of sites, pretty much all of the worker nodes we spec in the Midwest Tier 2 have 2 gigabytes of memory per job slot. It's just one of the defining properties of how we buy hardware. The IT services cluster that is a member of UC3 has, some have 2 and some have 3, I believe, gigabytes. So if your job has a requirement of more memory than just 2 gigabytes, you can set a requirement. I need this to run on a machine with at least 3 gigs of memory. And Condor will figure out what machines in the entire environment are available to run that through needs of the Condor class ad system. So we're going to do a very simple one here. We're going to set a requirement. This is, again, the same submit file, except we're changing the arguments to 1. We'll sleep for 1 second because we don't want this to take very long. Q25 jobs, but we're going to require that this job runs on a machine that has Atlas Tier 3 data. This is a class ad that we've set up that is advertised only by the worker nodes in the Tier 3. So you can set this requirement if you need direct access to the Tier 3 file system. When we run that, Condor submit tutorial 04. Um, 87503, we'll just do the Condor ID. Wait for that to finish. These are still idle right now, but once they get running, they're going to just fly off because they're only working for 1 second. Now it does take potentially a little bit longer when you put job requirements into your submit file. Condor has to do a little bit more work to figure out where those jobs are going to run, and it needs to send the jobs over to remote systems, especially if you have a large amount of material in your directory, data files that you need to send with your job or software that you can send with it. All that's got to get moved around to each of the endpoints that you're working on. So particularly if your requirements are such that, or conditions are such that you're flocking out to other sites, then it can take a little bit longer for this to engage. To see all the class ads offered. Um,
Condor status. So the resources advertised this Condor status. So how much memory? Requirements so that they can be attached. If you do a Condor status command, you actually.
Yeah, right. So I want to know what are all the clusters that I can get.
So you have to use Condor. So since Condor status is not showing you the other one we blocked. Condor complete val block 2. And a pool where
Underscore.
underscore. So now you have to do Condor status dash pool for each of those. It's not command grouping altogether. Each of those will show you.
We can script something together.
Yeah.
There's not a simple tool today to get lots of.
There will be. And still these are all the resources connected, right? You can use open science grid and the resources, and that's it's kind of difficult to go there because there is no direct way where you can start.
Don't want to go there, but maybe neighborhood here you might want to use.
So these jobs are maybe the environment just got a little bit busier. What's that? Ah, cool. So yeah, these are not going to run right now. We can just skip over it because the only point here was to illustrate the requirements mechanism. And obviously our requirement did not allow it to run on UC3 sub. So these jobs are going. We've kind of made the point from a separate direction.
We have another example, right?
Yeah.
High memory requirement.
Yeah, Lincoln is going to talk about requirements more. That was just the briefest introduction. We don't really need to look at the output, so we can leave those in there.
So this makes another really good point is that UC3 is actually you don't really have any control on. I mean, we do, but we're not reserving slots on the tier 3. Users actually have real.
Yeah, I mean, one of the principles is that we respect the local policies of whichever resource we're going to. Tier 3 is for the group, right? So already if they're busy with it, then any resource always whatever the policy is there.
So the last item in that, I guess there were two more points in the tutorial. One is that you can go to this job submission page for more information about job submission. And one of the things in there is a list of some different requirements that we can have. in a submit file. And I think we're going to make an effort to get the requirements that we have defined. Some cluster out there at another institution may advertise their own requirements that we don't really know about, keep track of. But anything that we've defined for the benefit of our users, we can put into a table here on the wiki and make sure that you know about it. The other thing was the cycle server site that Rob had a slide from there in his presentation, and Lincoln is going to look at that in a little bit more detail. So I'm not going to go into it right now, but there's a link to cycle server here and different utilization graphs. So if you want to come back and look at that after Lincoln talks about it, then these links are here in this tutorial. Okay. Any questions?
So now the next step is that we're going to scale up to more resources. So just carrying on with the theme here. And I'm going to go through basically the 5 different cases of what you might be thinking when you're submitting jobs. You want to send jobs out and under which.
I like to watch kind of when I'm doing this. We're running on this one. Let me just set this up.
The terminal we have on the one thing that you could pull from what Lincoln just did is you can actually watch other people's jobs.
Yeah, if you want to be really creepy, you can do that. I do that all the time. But so anyway, so we submitted what on the order of, I don't know, 100 jobs at most with this, but all connected all these resources connected together, we have some over 7,000 CPUs that are potentially available for you. So this tutorial is just sort of scaling up and seeing what we can actually access. Now I think I see over there that there's a lot of jobs in idle state right now. We did just hit a wave of load, so that's kind of interesting. So anyway,
Those are tutorial themes.
yeah, those are. Am I in the right spot? What's that? Yeah, those. Yeah, I think those I believe are all. Yeah. So those are moved. Okay, so so we have a number of cases when you want to scale up, because there's some considerations that you need to think about. One of which is we've been submitting short jobs that do a hello world and print the environment and all that fun stuff. But what happens if you actually have to read data or deal with data in some way? So do you read that data remotely? If so, how do you do that? Or is your data small enough to take it with you? And then the question that leads from that is, what is small? What is big? Very philosophical, but and then you get into the questions of sort of the same thing with software. What kind of software can you expect at a remote site? It may be very natural for you to have a GCC compiler on your machine that you work on normally, but can you really expect that somewhere out on the grid? So you kind of have to think about these things and think about how you want to deal with this. So we have the first, the naive case, right, of I can run anywhere. And we have this short job that you'll all get very tired of seeing by the end of this tutorial. So I've got this here, and I'm gonna maybe live dangerously a little bit and do all this live. So actually, for this one, what I did was if you look at short, it's the same short script as before, and I have a submit script here. What I did was I said I want to make the argument 600 seconds. So let's let this sucker run for 10 minutes. And let's queue up, I don't know, I originally queued up 2,500 of them, and I just wanted to see what happened. Fortunately, Condor handled it like a champ, but yeah. So you can try this as well, but this might take a little bit of time to run. So if you queue them up, let me do a tutorial. What is this one? Scaling, I believe. I set up this directory. I have all my stuff here. If I do, let's see what this short.sub looks like. I'm gonna make a whole bunch of dots, and they all appeared there in the Condor queue. And some of these may start up. We have a bunch idle, so fortunately we have a lot of free slots on Midwest Tier 2 right now, so we might see these actually start up. But you know, while we let that grind for a bit, I'm gonna take a look at some historical stuff I did. So when I was doing this, I submitted 2,500 jobs, and I was able to get 1,135 simultaneous. So that's all to run because it'll probably take forever and clog up the cluster. So you may just want to Condor RM those if you're following along. So another case is you know, as David mentioned, we have one CPU for every 2 gigs of RAM. Usually, that's sort of the Atlas standard, but that may not be your standard. So suppose you want to submit a job that needs about 2.5 gigs of RAM. That's really easy to do in Condor. You just say request memory. And if I do a request memory and try this, I think I called this high-mem.sub. Get there. Play with them a bit. Anyway, we just do request memory 2536. This is memory in megabytes. And I queue 100 of them. We can let those go, see what happens. So when I did this before, I used this distribution code with some cuts and some shell magic to figure out where these went, and these all went to the ITSF cloud. So Condor realized that we needed more than 2 gigs of RAM per job, saw that none of the other resources matched that, and sent it to the IT services machines. So this is really nice. It will just leave them in idle state. Condor will not even try to run it for you. So, yes, it should. We can try it live if you'd like, but
So it leaves it in an idle state because Condor never knows what machine is going to appear. I know why.
let me Condor RM my. Oops. So there's this really cool tool with Condor called Better Analyze, and it'll tell you why your job isn't going, which is really neat. Except it probably doesn't even. It hasn't tried to do this yet. Oops. So it says 6 reject a job by their own requirements. That's those are the jobs in the tutorial queue. So it does tell you what resources you defined here. It says that you tried to. Whoops, I'm really bad with mice. It says you tried to request 4 gigs of RAM. It will sometimes give you a suggestion, but in this case, it may not. This is one of the hazards of trying to do things live. So, but rest assured that is what it does. I promise. So I'll remove those jumps too, because those ones will never run.
One of the problems that basically you will have to go out and blocking mechanism is they don't work. One can match, try the next. Otherwise, you go through all possible places where
Analyze it to give you output.
it's giving you output for what has been tried so far.
This is using up the seeder, so I tried it. All right. So, informed that the cluster is very full right now. So, I'm sorry if your job's sitting idle for a bit. So another case is, what if you need to run specific software, right? So I brought up before that you may need GCC in your environment, but that is definitely not guaranteed at a remote site. Or you may need I don't know, Python 2.7 or something, right? So what you can do is you can use these Condor class adds that were mentioned before, and you can try to use a requirements line, and we've defined some of these class adds, and you'll see one for CVMFS later. But in this particular example, I use has Mathematica. So some of these nodes in the seeder have Mathematica locally installed on them. So I have a requirement of has Mathematica equals true, and I submit these jobs. And again, I am under the impression that the seeder is rather full right now, so we can do a dash pool management. We can see that all the slots are claimed right now, so we'll work on fixing that after the talk. But anyway, so unfortunately, these jobs might take a little bit to get through if you submit them. But I went ahead and I did this, and I did a distribution, and you see that they all ran on the UC3 seeder. None of them tried to run anywhere else because we have a class add that says you must run on a node that has Mathematica. So that's one way you can make sure that nodes run on software. Yes. Mm-hmm. Right. Yeah. So we have a solution. We think the solution is CVMFS, which is the CERN Virtual Machine File System. So the way it works right now is you come to us and you say, "Hey, Lincoln, I need all of this stuff installed into CVMFS." And I say, "Okay," and I compile it for you and I get it in there, and I make a little area just for you that has all the stuff that you need. And then that CVMFS file system is mounted on a lot of nodes, but even where it's not mounted, you'll be able to access that. And that's actually something that Suchandra is going to talk about a little bit later. We've come up with we've devised a method to make CVMFS very portable. So we're hoping that we can take all these cases and then collapse them down into the first case of I can run anywhere. That's what we'd like to see eventually.
So if you just say has Mathematica,
Uh-huh.
you don't say where you want to run, how do you know out in the world
That's possible, I suppose. I don't know.
You know.
We'll get there when we get there.
Actually, the class-side matching not for once you got to OSG, if someone else, because in OSG you have Condor, you have PBS, you have other manager.
So they may not even have class ads where you're ending up.
If that's not on the site in Texas where we are running the jobs, will not be available for us.
Basically, you can only allow jobs to plug out to OSG that have no specific requirements.
There you go.
The requirements of some of which I read.
Yeah, yeah.
And whatever.
About CVMFS, what about it? So OSG is not, or OSG does not natively mount CVMFS, but you will be able to access it with this really cool thing called Parrot, and you'll actually get to see that. We actually, just for you, Sam, we run a root job on OSG with Parrot and all that stuff. Okay, so we have the fourth case here, and this is actually kind of what David just did. And we know the tier 3 is full right now, so we probably won't even bother running this one. The tier 3 is full too. Yeah. So this is, I need my data and CPU to be co-located. Actually, in your printout, it probably says collocated because I didn't know those were two different words. But anyway, so you can use these requirements like has tier 3 data. And this is sort of what David did in the previous tutorial, so I'm just going to kind of breeze through this. I did make a different script, so you actually do, in the world of scripts, there is something other than short.sh. And this just copies a file out of my area on the UC tier 3. Just copies a 100 meg test file back to the worker node. And then Condor will actually transfer that back to the submit host. And I show that here, because after the job finished, you see that there's this lincoln.test.100 MB. So that file was copied out of the tier 3 data share and then copied with Condor's mechanisms back to my submission dir. The final case here is I want to use the grid, because all of those resources are out there and they're idle, we want to use them. So the only thing that's different here is that you have this funny looking requirements line, but I promise it makes the jobs go out onto the grid. And you have to be very considerate when you want to use the grid, because you need to think about these things I brought up before. What software is installed on the grid? Probably not much. How do I get my data? Am I guaranteed scratch space? I need to think about these. So I did try to submit some boring short.sh jobs out to the grid, and I got some pretty decent results. What I did this time was there's an environment variable I learned that is set by sites in OSG called OSG site name, which is really helpful because it tells you where your job ran. And I see that most of my jobs actually just ran at Midwest Tier 2. And Midwest Tier 2 is split up here into a couple pieces. You see there's a UC component and an IU component. Because it's actually spread across 3 different sites. So that's why you see it 3 times here. And we also see that our jobs ran at Michigan, and we also see that they ran at Texas Tech, I believe, assuming that's what that 3-letter acronym is. So yeah, and Marco posted a really nice little picture here of this is the Glide in WMS front end, and you can go to this and look at it, see stuff happening. Marco Suchandra? I don't know.
Yeah.
I see.
So if you find some OSG sites that have the things you need,
Right.
Yeah.
There you go. So that's all I had for this tutorial. So I'm sorry that none of the jobs probably were very successful in getting submitted. I'll work on that right after this. But does anybody have any other questions?
Okay, so yeah, so I think you know, as we go through this, this tutorial, of course, is going to be there for a while. We're going to continue to refine it and little problems that there probably are in there. Hoping that you go away with this with enough of an introduction that you can come back to it and try these examples. The next one. That's one of the reasons we forced ourselves to have this workshop, was to create this documentation. We're gonna, yeah. So this will be the first place to stop. Let's see, so we are almost. We're at 10:30. Do we want to take a 5 or 10 minute break, or do you guys want to keep going? Or there'll be stuff outside.
Marco's finish up session 1.
Great idea. Okay. So Marco is going to discuss some of you may have accounts on Midway, and also how to actually access, so you can access, but also you might want to just access it directly from your laptop.
So there is this tool called Bosco that allows to connect hosts to any other machine, other resources, and works on Mac laptop or Red Hat 5, 6, or Debian. So if you have your own desktop with Linux or a laptop with Linux or Mac, and you want to submit jobs from there without having to SSH to UC3 Sub, you can do that. And the same if you have an account on Midway. So for this example, I'll have here two actual terminal. One, I leave the one that I had before on UC3 open there. Later you'll see why. And with the new one, I will, so I have an account on Midway, so I will SSH to my account on Midway, and I'll do the example on Midway. If you want, just open a terminal on your Mac, and you do exactly the same command from there and install it on the Mac, so that there are many Mac in the room.
Account on Midway already. Everybody's, so let's focus. Yeah, let's focus maybe if you want a preference, one or the other, probably Mac.
Right. Because I was showing the example also submitted to Midway that I can do. But it will be exactly the same. So ignore this SSH that I'm doing in the beginning.
Just to clarify here a little bit more, the idea that we're thinking is that we have the RCC is sort of like the research computing center, and expect that a lot of users will clusters, but if you are in that environment, what Fausto will allow you to do is to submit a set of jobs that will go to Midway, but also will come over to UC3, able to do sort of both. Now, that's not necessary if you're already in UC3. You can schedule up.
So the idea is to use something that you are familiar with. So you don't have to move away with your own whatever you use your own machine, whether it's your laptop, whether it's Midway, or whether it's another desktop where you log in every day and you use. So you have there your editor, you have there the programs that you like to run already installed. So you can use that, and from that machine, issue the command to send the job to UC3. So for everyone from the terminal, you can, so for this tutorial, since it's an unknown environment, it's not UC3 sub, so most things you have to type or copy and paste. There will be not much set up in the tutorial. So just download this quick start. It's an installer for this program called Bosco. So I'll just type the line with the curl command that will work both on the Mac and on Midway. So I'm typing that. And this is downloading a file. If I do less, you can see that I have this file now in my directory. And then I'm running the file with bash or a shell, both will work. So the first thing that the installer is saying, I don't see that you have Bosco already installed. Do you want to install? Just press yes, and let it install Bosco. Yes, on the Mac. So it'll be fine. Just open a terminal. You know all how to open the terminal on the Mac. So on the, if it's not in your menu on the bottom, you go in the application. So in the application under utilities, there is the terminal. So that's what you have to start on the Mac. And then once you have the terminal, the command line, just type this or copy and paste from the web page. So in the meantime, Bosco was installed on the machine. Ignore the SSH. So just keep it, just do it from the terminal. So I could actually. So here, this terminal is on the Mac, right? I just opened the terminal. On the Mac, I just opened the terminal window, and I run the CRI command, and then I type bash Bosco quick start. Okay, and that's installing it on the Mac. It's a no, it's a shell script. So you have to invoke with a. Did you? Okay, the other people, did you get to the installation? So some browser, if you you have a narrow window, they don't show the whole line. So make sure that you have the whole line until the Bosco quick start. So after you have actually.
So is this like?
This is installing. So this is installing this program that's a Bosco. It's kind of like a personal Condor installation, and installing the subdirectory Bosco of your home directory. Okay. So I'll show you once it's installed. So once installed locally, I ask it to connect I want it to connect to submit job to UC3 sub. Okay. So it's telling me where do I want to connect. So I enter there the name UC3 sub .uchicago.edu. And then it's telling me what's the username on that machine. My CNET ID is MMB, so it's already there by default. Or if it's telling you something different, you can just go and type your CNET ID there. And then it's asking what queue manager is using this machine. So I could connect to other resources, but UC3 sub is using Condor, so I type here Condor. Now it's connecting there and it's asking me for the password on UC3 sub. So it's my CNET ID password. Once I enter my password, this will take a bit. It's going to UC3 sub and install some file in the subdirectory Bosco of my home directory there. And this will allow the connection, the possibility to submit jobs to UC3 sub.
So if you're on UC3 sub, you should.
Yes. So if I go, those are in subdirectory of your Bosco directory.
That's a little bit subtle, right? So you're on your laptop and you're downloading this and you're installing it on your laptop, but it's actually installing things on your target. Installing things in two places.
So Bosco is quite generic, allows also to connect to multiple places. Here in this tutorial, we'll be just connecting to UC3 sub. So this might take a couple of minutes. Yeah, just to explain you what's happening, so you have installed a personal Bosco on your laptop and installed some file that allow to connect and run jobs on UC3 sub. And then you will basically be able to run all your command locally on the laptop, and this will submit a job remotely. So after installing the Bosco there, what it's doing is submitting also a test job to make sure that everything works. And if there are some error, will tell me what is wrong, like not enough space on the disk, or there is some firewall problem. We'll try to diagnose which are the problem.
I'm getting
Minus. I tried on the Mac, and usually it's just printing the dot, but I'll be curious to see it later to see why the echo is pointing that. Anyway, when it's completing the test, it will print you a couple of suggestions. Here is a link to the communication for Bosco. Here is a command that you have to do. So Bosco is set up in your Bosco subdirectory, your home directory, but it's not in your default environment, so it's not disturbing. Normally, you can do your own commands. It will just use some space in your home directory. If you want to use it, you have to source a setup script and use it. And once you don't like it, you want to remove it, you just source it up and then you can install it. And here there is a suggestion on what would look like the submit file that you could use to submit file with Bosco. So it's printing it there on the screen. So what we will do now, we'll submit our short file. So I'm making a tutorial directory. Ready. And I cd into the directory. And here I will copy the content that I have from the web page with our usual short job. So I use VI. Once I start VI, I press the key E for insert, I for insert. And then I can paste the content. And then if you're not familiar with VI, to quit, you can press the column and then W and Q. It's writing and quitting. Then I will edit also the file bosco01.sub. So if you're on the Mac, you can use your text editor to edit this file, and this will work as well. And here I'm pasting the content from the submit file on the example on the web page. Yes. So no, sorry, there is no unit. Oh, the accounting group. Yeah. So I'm editing submit file, and in the accounting group. So yes. So all the jobs that use Bosco will use the grid universe. So the grid universe is used for by Condor to submit jobs that are not running on your local machine. So with Bosco, what you use it as a gateway to send somewhere else. In this case, UC3 sub. And so the jobs have to be in the universe grid. Normally, with the universe grid, you have to specify also where you run. But by default, we'll send jobs to the cluster that you entered in the grid. So if you just specify the universe vanilla grid, your jobs will end up on you want to make the log directory. Yeah. And then you can submit the jobs. So I just in the directory. In the submit file, yes. It's the only thing different.
Like when I'm
yes. The other difference is that, of course, I mean, you have your local directory, your local file are the one on your Mac on your server, and not the one on UC3 sub. So the submit directory where the output and the log will come back. It's
But if I submit jobs,
yes, everything.
why would you ever? Bosco, no.
No, the Bosco is connecting you to all. It's not a subset. So when you connect to UC3 sub, you reach everything, Midway and all the other nodes. With Bosco, you reach exactly the same. So with the jobs that, in the example before that David and Lincoln were submitting, they were going on the local machine, on Cedar, on Midway, on OSG. That's by submitting the jobs on UC3 sub. If you don't that, what will restrict where your job runs is eventually your requirement line. If you have a requirement, you can say I want to run only here, and then that's okay. You're limited. But if you don't leave the requirement, UC3 sub is connected to all the resources. When the one that showed before the plug 2.
I thought we needed.
So
On that original slide.
So that's a
My
different.
box inside the system.
So Bosco can be used to have your own personal condor. That's how you use it here. Or can be used by UC3 to connect to some other resource. So within UC3, there is another Bosco. So there is.
Oh, okay.
The Bosco service that's handling multiple people bidding on your behalf.
So when I submit from UC. Yeah, okay, I'm fine. Okay. Bosco is the version.
Well, I mean, so Bosco, this is always confusing. I mean, Bosco is set up primarily. It was developed principally for with the user focus. So here's Bosco, submit from your laptop and go anywhere. But it also is set up as a service, which you don't have to actually download or install Bosco.
So here, something that I did as a mistake. I didn't source the setup file as instructed. So each time I have to use Bosco, I have to source the environment file. So I wasn't able to con. I didn't.
Set up some files in my home directory on UC3 when I install it with UC3 as the target.
Yes.
When I submit jobs through that, process goes through UC3 sub.
So the submit process starts in your laptop or your machine, goes to UC3 sub, and from there it is spun out to all the resources that are
Like
connected.
the file transfers that happen, do those go directly from my laptop to the end node?
Depend, the files that are in your submit directory on your laptop go to the node, directly to the end node. Are sent, actually no,
You're
sorry.
using the file
No,
transfer
go through sub. If you use the Bosco transfer, they go through UC3 sub. So from here they go to UC3 sub, and from there they are sent to the machine where they are running. And the good thing is that using the grid universe, the connection is one way from your laptop through to the UC3 sub through SSH, tunneled in SSH. So that means that will work anywhere you can SSH UC3 sub. You are on a Starbucks, on a Wi-Fi, under a NAT. If you can SSH out, will work. There is no problem of firewall blocking connection in or looking things in your machine. All the connection use the SSH tunnel.
If I create they finish?
So Condor will restart and check the status of your job once you open your laptop and transfer your stuff back. And
We'll get your log files back later.
you will get your log files back.
So the files are sitting there on UC3 sub waiting for you to connect to your copy.
So
Does that lock those notes?
no, so the nodes transfer to UC3 sub, and then we'll get the file back. Condor the mechanism. If machines goes down, in theory, Condor is reliable. If machines goes down, so there might be cases where you might lose some of the file if something on the other end also went wrong, besides closing your machine, your house. What'd you say?
How long are the files kept?
They are forever until you connect. Yeah. So what I do in the second example. So here for people, so you said there is someone that has account on Midway. You have. So what I'm doing here, I'm submitting the same executable also to Midway. And the submit file is similar. So I have a local queue in the machine where I'm installed Bosco. And like on Midway. And
You can follow along if they have an account. Copy the file.
if you have an account on RCC, you can copy the file and
Copying what?
to bosco02.sub. And you can leave it as it is. So the accounting group and the tutorial job, these are significant, meaningful only for UC3 sub. So when you submit locally to Midway, they will just be ignored. So you can leave them there. And the important line to pay attention to is this line that I add, saying that the grid resource now is the local batch system, that's PBS. On Midway, there is actually Slurm, but it's used by Bosco by using the PBS emulation.
Right now, I copied Bosco 01 sub Bosco. I have this line here, right?
This,
You just told me
yeah,
I didn't have to
yes.
do anything.
Yes, there is a Bosco 2 in the web page. Oh. I'm not. So and I submitted the file.
Okay, I'm sorry. So
That was a submit to Midway. That's the first step.
replace the contents
So the content of Bosco2.sub, it's the one that's on the web page, and it's
just out of curiosity, why did you ask me to copy Bosco 01
because that's exactly what this is doing. I could say just to copy and paste from the page. Yeah, sorry. The file Bosco2 is
copied it.
and then add the line. So what I'm doing now to close the presentation is I will submit in multiple jobs, and I want to send 20 jobs each with a sleep time a little bit longer so that I will see that they are running. And what I do, I will edit the submit file that I have. So if you are on RCC, you can edit both Bosco 2 and Bosco 1. If you are on your laptop, just edit Bosco 1. And what I'm doing, I'm adding one line with the suggestion in the web page with the line arguments equal 40. This tells to our short.sh to sleep for 40 seconds instead of just 15 of the default. And then I'm changing the number after queue command to 20 to tell Bosco to queue the 20 jobs instead of just a single one. So I'll be doing the same. Now if I submit the file Bosco 2 and Bosco 1, I will have jobs queued in my local queue, both on Midway and on UC3 sub. There is a attribute on the Condor queue command, that's -grid, that will actually tell you where the jobs are running. So if I watch now my jobs, I have some in the yes queue. And yeah, and these jobs will be just, so other thing to note here is that I use just Condor queue without adding my ID. Because Bosco is my own personal installation. So if I show the queue here, I see only my jobs. If I go back to the terminal that I had before so this was the terminal on UC3 sub. If I issue just the Condor Q command here, I will see jobs also from all the other users. While in my Bosco one, I was seeing only mine. So it's also a tool that allows you to simply separate your job and be more aware of what you are doing besides running on your front-end one. So in my terminal, I was logged in Midway. That's a cluster that has a big Slurm queue. So the Slurm has a PBS simulation, and that's what Bosco is using to submit jobs there because it's not talking directly to Slurm. So the grid resource, it's a line. So in Bosco, in the meantime, some jobs completed and are queued. So in Bosco, we went to the quick start where we added UC3 sub. There is a Bosco command that's Bosco cluster add, where you can add other resources. So you could add from directly from your laptop, you could fan out directly to multiple Condor PBS or C cluster. And if you want to submit jobs to all of them, Condor, if you just submit a vanilla job, Bosco will send a glide bean and allow you to go to all of them. But this has some extra requirement. If you use the glide bean, then there might be firewall problem. It's not working well behind the NAS. So what we use with the grid universe, we target one resource at a time. So in the submit file, you can send jobs. You have to tell where to send. By default, it's sending them to the first one. That in our case is UC3 sub. But you can, if you connected more than one, you can have grid resource and could be fetch the name of the queue manager used there, Condor PBS or whatever, and then the host name and the username. So if I want to what I'll show you here. So in my home directory, in the Bosco directory, is where my personal condor is installed in the sub. And there is a file that's basically saying, setting some default for my condor submit command. And if you send a job to the grid universe, but you don't specify where you want to send it by default to. So that's explaining what's behind the scene. So in the submit one, I just specify grid universe, but nothing else. So Bosco is sending it. If I specify a line with grid resources, something different in my submit file, we send it there. If you don't have that resource added and connected to your Bosco, then we will get an error. But if it's added there, the job's. Yes, exactly. So basically, the jobs that I sent before in the queue, some went to UC3, but then it might also go back to Midway through UC3. But the one, since I'm already there, I said, okay, so I'm sending them directly. So if you are like on the TT cluster and looking on your login node there, you can add directly your tier 3 and UC3. So you can submit jobs to both from your own personal. Of course, the tier 3 cluster is used also for opportunistic jobs for by UC3, right? But if you submit directly, use your own username account, your own priority. So you might run faster than.
So you finished?
I'm finished.
So why don't we take a 10-minute break? Back to distributed software data access.
One thing I'd like to mention actually before we get started, online with the material that's on the website is any login set. Other comments on the material.
So I think
Yeah.
not on very
Work on it, but I don't want to have to go to Midway.
I should probably. Well, the thing is that let me going through it. It exactly is. How's that work? So I'm just in a flow chart, right? I know the key breakdown. On my laptop, I can break down. But this should be
Um,
on my laptop. Maybe we need to make a new laptop. Yes. No, I think we should. Maybe we need this. I mean, in other words, like trying to put two of them into one page. Create a trash. I'm following this. I'm following it as like a monkey. A monkey is following it. Because at the beginning I said if you're on a company, yeah. Yeah, but I also have a laptop. So if you're saying that you must box it, I think you probably if you haven't contacted me, if you're not going to. Well, I mean, you're going through this real time, and then I'm following you. Like, I miss that. Maybe you know, you say I can't rely on everybody to. I don't know. Just to make it clear, I should be able to. Now I mean,
you can do it.
yeah. So I think
That's a little bit more complicated.
so. This, I mean, now. The other thing that happens here is that's pulled into a lot of very technical stuff. So in other words, I think that we need somewhere in this. So if you're just plugging in UC3 and Boston, but if you're just now you're saying, okay, I want to use Boston users now. Then I think it requires a little bit more.
Stephen has Ubuntu on his laptop, so he tried to install Bosco on SPT Cloud or Linux server. All use all the time as an interactive machine.
So it's supporting Debian 6. I don't know. Ubuntu depend on the version, might or might not.
Yeah, he wasn't trying to do Ubuntu. So it's CentOS 6 that's running on SPT Cloud.
Okay.
And when he tried to install it, it complained that it couldn't set up the SSH key on UC3 sub.
So Rob, what are we doing next?
I mean, we don't want to spend a lot of time on it now, but I was wondering if you had any
We should be
idea.
going, I think, to Suchanga stuff next, right?
I think my stuff is next. That's
Oh,
where
okay.
that was
Oh,
my
that's right.
question.
Yeah, forgot it.
Yeah, so I didn't know if you.
No, let's keep going.
Okay.
I think we should reinforce things here. Remember, we only have an hour left
Yeah, I know that's why.
before Mike. So maybe you do one of these.
Okay.
Maybe just do R.
Okay.
And then Suchanga, you'll probably get through software access.
Yeah. Okay.
And
then we can.
that's where
we
we
probably
end,
should.
right?
Yeah. Okay. That sounds good. Or I could just do the root
So
example.
the midway, we need to, I think for the midway, for the Bosco stuff, I think we should split this into two. It's too confusing. Like right now as it's written, it basically, I mean, right now as it's written, it leads you into a trap. If you're starting from your laptop, I mean, I try to submit jobs to midway from my laptop because I have an RCC account, right? I got clobbered. Yeah, I got all my jobs went into health state, right? So we need to split that into two. And we probably need a little bit of narrative about this conversation between Marco and Sam about how, about how jobs are getting to where. I think we need a little diagram or something. Yeah. So unfortunately, I explained this to Marco.
Are there other people in the
I mean, basically, it's
So the PDF for this book.
okay, yeah, yeah. But
Or well, we would use that too.
I like this. Um. If you have any.
Yeah, all this is, I think we're probably just gonna archive it, and then we're also gonna continue to evolve. Well, you know.
Links to YouTube
if-
videos.
If we think that your comments are lighthearted, we may respond.
All right. Yeah, it's basically what I've been like.
You've been discovering sort of.
I've been like, oh yeah, I'll just update. All institutes that they also have some. That's really nice. The way they're doing this. As far as I can tell, they pick up book.
Yeah.
And then go through.
So you just need access.
They don't even need to. They have all of them open.
Oh, okay.
So,
They just
but what they,
distribute the documents to all the nodes.
yeah, but what they're doing now, yeah. Okay. So, how do you feel about it? Okay, yeah. Oh, wait, article. No, this might not be the same thing. At the university? Oh, no, so this is English. And you might be, I mean. But, yeah, but I'm meeting with them tomorrow. Yeah, Google has something like that. But what they want to do then, they want to find the way. They want to see. Find the
So all
stuff.
Google gives you is raw.
Yeah,
Instagram.
So they like basically they set up on Instagram, and now what they want to do is run through again and say, hey, words are weird.
Yeah.
Like,
Totally agree. There's a lot of work to do.
Yeah. It comes from that. So they want to.
Every time he tries to
Yeah.
one off.
So basically, even if it comes with an idea, a week for it to run through and get.
You're saying how many deliveries?
They have, I don't know, I asked them. So they're 360
Montenegro chocolate test.
but they have them. Well, I can't imagine.
He's the man of the 21st century.
Probably don't want to make it right easy.
That'd be cool. Like in, what's that movie? Demolition Man. Demolition Man. Nobody's ever seen the movie?
Well, it's a fair amount of transformation.
In Demolition Man, it's the far from future where Taco Bell owns the fast food wars and all food systems.
Yeah,
then you're accidentally.
But it's the ideal. No, I think we're.
All they need is.
It's a supply and demand. Yeah, no, it's not. You go back to
I would just.
G, right now, I don't know, it's small enough.
Yeah, when I, we have less than an hour.
It can just down. I do, yeah, it's got.
You just do R.
Ours not all it is.
You wanna do, or you wanna go down to root?
I can do root,
Yeah.
but I don't, yeah, I'll do root.
Okay, so we are gonna improvise a little bit here. We've got more on the program here than we have time, obviously. So we're gonna skip down to section 4, and we're gonna run root on UC3. How far and wide we can go.
We'll see if it works.
See if it works.
Okay. Could we put the Condor Q back up, Marco? That'd be really cool. Okay. Are we still logged into? I'm just gonna log in as me, I guess. Oh, I see. Okay. Sorry, I'm a bit slow. So I'm gonna just load up the root tutorial. And I guess Suchandra will talk about this a bit more. So what we're going to do in this example is we're going to use root, which is a data analysis framework used in high energy physics. And we're going to assume that you've been introduced to CVMFS and all that good stuff. So we've taken the liberty of taking root and putting it into CVMFS so you can access it. And this actually comes out of the Atlas CVMFS, which we use on Midwest Tier 2 quite extensively. So we have this little file that sort of just sets up root for you. It's called environment.sh, and it just does some pretty simple stuff. It sets up GCC in the root environment and this file access protocol called xrootd, which can read files remotely. So we're going to try to source environment.sh. That seems to run. Now let's see if we can run root. Now I run root-l because I don't want the splash screen because I don't have X11 running. And just to prove that there aren't any tricks up my sleeve, I'll try to do a witch root. And you can see that's running out of CVMFS. I didn't install it locally. So that's pretty neat. That's basically this first part here. So there's this, we have this root code as well. I guess it takes a root file and inspects it and looks at all the trees and branches inside of it and does rooty things. So I actually shamelessly stole this from Ilya, who's sitting in the back there. It also comes with a handy dandy make file, so you can compile this down into executable code. So if we try to run a make, should make it. Seems like it did. And there's just a lot of stuff here. So I want to actually try to run this, see if it works. So what I'm doing here is I'm giving it a root uniform resource locator, I think that's what that's called. So it's going to read data out of the UC Tier 3 xrootd file system. Let's see if it goes. It went very fast. Very nice, actually. And it printed out all this stuff about this root file that I stole from some poor graduate student. And that seems to... So that root file is actually located on one of 3 file servers sitting in the basement of Accelerator. And so xrootd is its own, I guess, fancy file system and file access protocol that's used by root code. So I don't actually know a whole lot about xrootd other than the fact that it just gives you a method for accessing files remotely. And I think this code actually reads it. It doesn't copy the file; it reads it remotely on the server. Is that right, Ilya? Yeah. So it's kind of interesting. This is really cool, and we can run this code anywhere. But we need to have root. So to do that, we use Parrot, and Parrot does some really fancy stuff where you make a system call and it intercepts it, and then it can talk CVMFS natively. So I've written a little wrapper script to do this, to set up Parrot for you, and it uses, I think, some LD preload magic if you're familiar with LD preload, and CVMFS is really cool because it has a lot of caching stuff. So it caches against an HTTP proxy, which we export here, and it also does local caching on the node itself. So if you set up software via CVMFS, it gets cached in a couple of places. So it's kind of nice for performance. I guess I actually have this wrapper script already. So there's this big crazy looking line here, and this is where the Parrot magic happens. So this, I guess, will load this CVMFS repository, and then it will hit our Squid cache, which is an HTTP cache, and get the root software and all the stuff that we set up. And then it just runs. This bit is that code we just ran. So yeah.
So if I run
Yeah.
on my local,
Yeah.
then at the end of it,
On your local machine. What, you mean your Mac?
yeah.
So I'm not sure how well Parrot will work on your Mac. It won't. That's the answer.
Using,
So Parrot is a Linux application.
and what if I,
So if you logged into some Linux machine and ran Parrot, it would set up CVMFS for that job. It wouldn't have it natively mounted. I mean, you couldn't ls CVMFS after you did that. You'd have to do everything inside of this Parrot command.
what if I just,
Yeah.
so when I go
Hmm?
there, on that,
And do your Atlas setup stuff. That will work. So we actually found a bug with, well, it's not a bug, but it's just it's a thing with, if you do like a local setup Atlas, it'll be really slow. It'll just take forever, I guess, because it's doing some finds and magic stuff underneath. So because it's trying to touch so many files and then intercept all of those system calls, it becomes very slow. So we've tried to do the bare bones root setup.
And I think, ultimately we would like to support many different Atlas job types in this fashion, but these reasons, I mean, it's said that, if you use the Atlas local root base package, it doesn't work very well. So you should be able to get to root. The only problem is that. If you know exactly what kind of environment you need to set up, then you're pretty much good to go. So lightweight root examples, like anything you'd be doing in prun, you're not setting up some Atlas environment.
well, I was thinking. I was just, but if we set up
If you grab it from the Atlas CVMFS, yes. There's also some versions of Python in the UC3 CVMFS. So anyway, yeah. So we ran this wrapper script, and it had the same output as before. And okay, there's my terminal window. So it looks like it worked. In this particular example, I submitted it out to the grid. It does take a little while for these grid jobs to spin up. The grid is really nice when you have a whole bunch of jobs and you can sort of submit 1,000 jobs to the grid and then go take a nap and then come back and they're done. So it's unfortunately not too, the turnaround time isn't too fast when we want to try to submit these in a live demo. But I can try to do, so we'll look at the root submit file. The only requirement I had here was this is undefined stuff, and that's just to make sure it goes out to OSG. And we could totally remove that if we wanted to. In fact, I will. Our job should work. So I just remove the requirements line, and I try to convert submit root.submit. It's an idle state, and it should fire up at some point soon. So I just wanted to look at the output of that. This is a job I did run on the grid, and this job landed at the Atlas Great Lakes Tier 2, and it ran, and it printed out all these T trees and branches for our root code. Reading that out of the UC3 Xroot D system, sitting in Accelerator. So it's pretty neat. You can basically use this with any kind of job. So we're doing all this setup for the SPT folks, and we hope that we can run your jobs that way too. Run them out on the grid.
Questions? All right. Okay, so that's there. Again, come back to this tutorial at your leisure, try things out. And as I was mentioning, we've mentioned it a couple of times, but just to reinforce it, as you're going through these examples, these tutorials, we are interested in finding and fixing problems. And since you have a CNET ID, you can log into this wiki, and you can leave a comment at the bottom. You can add a comment. So any question or anything like that comes up as you're going through, this wasn't clear, or I found a mistake here, just post a comment there. And then... Great, thank you, Lincoln. All right, so we're going to go back to, there are a couple of other examples there using R on UC3, using mathematics that are kind of fun. Now, Suchandra is going to talk more generally about software access in the UC3 environment. It's essentially the same story that Lincoln just described or demonstrated. So there's software, and there's also data access as well. The data access with, if everyone were using Xroot D, would actually be quite nice. We have a solution for that. But since that's limited only to high energy, we have to have some other options here, and that's why we have Chirp and Focus Online. Why don't we just go in order here? So
Okay.
Let's go to software access.
All right, so so I'm going to be talking about a few different methods of accessing software or getting software on nodes if the node doesn't have it. So basically, like Ken mentioned, and in general, you can't necessarily depend on all of the software that you need being on nodes that your jobs land on. So there are a few different ways of ensuring that you actually have the software that you need. So first of all, let me just get a terminal up and right. So I have a little work environment all set up. Okay, and beyond this, I'm actually going to be setting up the public HTML directory. This comes in handy a little later on for this and for other methods because some of the methods actually go out to web servers to download application tarbals and We actually have our facility, UC3 Data, has web server running, and it's set to automatically share public HTML directories from user direct home directories. So if you put something there, you can then later on in your jobs and applications go to your public HTML directory or the web server and grab tarballs or other things that you stashed there. Right. So the first method I'm going to talk about is HT Condor file transfer method. So Condor actually has a built-in mechanism to transfer files back and forth. When you submit your job, what you need to do is you set up a few options in your submit file, and then when you do a Condor submit, Condor will then look at that, notice that you said that you wanted to transfer files, and it'll copy it into the worker node when your job starts. And optionally, you can have it copy output back to your submit node. So right. So the first, so here's the submit file. What you need to do is there should be transfer files. You have to set that to yes, and then you could specify transfer files using the transfer files option. You can actually specify directories there as well, so that and Condor will go in and recursively copy everything from that directory to your compute nodes. The one thing you do need to make sure is that the files that you specify are in the same directory that you submit the file in. So here, the file will need to be in this UC3 access directory. So I will be creating the test.sh and the directories that the file refers to. So there's the shell script. I'll create a directory and put a little hello world thing in there. Right. Now I will then go in and modify. Oh, yeah, it's CNET ID is fine, right? Using the this account. Okay. All right. So I'll just create a directory for the logs, and then I will do a Condor submit of the file. So let's see. Okay, so my jobs are all running, and they've completed. And if I go to the log directory, look at some of the output, you'll see that it actually did. It was able to cat that file, so Condor transferred the file there, and then when the shell script ran, it was able to find the hello world, the contents of the file in the test directory. So this is actually a pretty nice mechanism. It's actually built into Condor. It's pretty easy to use. You actually don't need to worry about anything. The one little caveat is that you should. This is great for quick and dirty jobs, but you need to make sure that you don't try to use this with large amounts of data. So if you have an application that's 2 gigabytes size, you probably don't want to be using this to copy things back and forth to all the worker nodes and all the job slots. So there's actually, I'll also, an alternative if the file transfer mechanism isn't something that you can use is distributing your applications using the web server. So as I mentioned, we have a web server on UC3 data that's serving the public HTML directories and home directory, user home directories. And I'll go through this, and this actually comes in handy for a slightly later module when you use Skeleton Key, because then you can use this and application tarballs that you stash in your home directory with Skeleton Key to get your application or data to machines that you run, that your jobs start running on. So that's right. So the first thing to look at is the submit script. So here it's basically the same, similar to the conduit transfer mechanism. I actually use the transfer mechanism to copy the executable over to the worker node when I start. The one little quirk is that you now need to create a shell script that will then, that when run will go off, create a little temporary working directory, copy your application tarball, extract it, and then run your real application. So here, the script just creates a temporary directory. It does a wget from the UC3 data server, and then it extracts it, goes into the directory that's been extracted from the tarball, and then runs the little hello world cat script. So at this point, let's go through the process of creating a little tarball. I'll create a little directory for the file, copy the shell script that I want, and then copy the tester there. And then finally, make sure that my shell script is executable. Fire everything up. Copy to public HTML directory. Make sure that it's world readable. And then I will create a submit file for this. Here, the executable I want is the little shell script that does the downloading and extraction. And then I'll do a condor submit. Right. So at this point, while it's sort of other jobs are being queued and run. Are people having issues, or is this working out all right? Okay, so the jobs have run. And if we look at the logs, see that the script was able to download and run the application. We got the same output as in the previous set of jobs. All right. So the other mechanism that you can use is when you have really large applications and applications that are used frequently. Things like Mathematica or MATLAB. And if that's the case, the best thing to use is CVMFS. So CVMFS stands for CERN VM File System. It's basically a way of distributing applications using a web server, and then those applications are presented as if they were locally mounted on machines running clients, or you can use something like Parrot or Skeleton Key to access it on machines that aren't running native clients. So in this example, I'll actually be running Mathematica, and I will be using the UC3 CVMFS repository. We have Mathematica as well as a few other bits of software installed there. So here is the submit file you use. The CVMFS repo is actually installed and mounted under /CVMFS repository name, and then there's the path here. I'll show you later on how you can determine what path to use for the software that you might be interested in. We'll have as the arguments, we'll just get the version, Mathematica version. So it'll be something I'll run fairly quickly. And finally, we have a requirements line that you'll need to use. So UC3 is sort of a federated group of clusters, and not all the clusters in the UC3 environment have a CVMFS installed, and so you need to use the class that has CVMFS equals true to make sure that you land on nodes that mount the UC3 CVMFS repository. And finally, we have a transfer executable equals false here, so that Condor doesn't try to get this Mathematica executable and copy it over. All right, so why don't we do a Condor submit. And it's running. At this point, any questions? All right, so if you look at the log files, yes, I think Lincoln cleared out the UC3 cycloseeder cluster. Okay, yeah. It ran Mathematica and got the version, just Mathematica dash version. So you just get the version number of Mathematica installed. And we have Mathematica version 8.0. All right, so I'll actually do this as well for R. And there's actually one little thing that we need to consider for R, where so Mathematica is actually written or written so that it is sort of self-contained and relocatable. And not all software is like that. R is actually one of those that is quite a bit different. And so what we need to do with R is set up a LD library path. So we have to modify the LD library path so that include the library path that R uses to libraries. This is because the default LE library path on machines don't include the CVMFS mounted library paths. And if you try to run applications from CVMFS without this change, sometimes the application will run. Other times, if it tries to use functions or things in dynamic linked libraries, then the application will crash. So we have a little wrapper script here that modifies the LD library path and then calls R. And here we actually, in R, we just calculate the eigenvectors of various, of a Hilbert matrix of various sizes, and then do some sorting of normal distribution vectors as well as do some fitting here. Right, so submit file for this is pretty much the same as the Mathematica example. We have the requirement that the node has to have CVMFS. Here we actually tell Condor to transfer the executable because we're not running R directly. We're actually running the wrapper script. And we're also having Condor transfer the R script as well, so that R will actually have something when it starts running. Right, so let's submit this. And it should start running fairly quickly. While it's running, any questions? And it actually takes a bit of time to run, so about another 20 or 30 seconds. So you don't need to have, the libraries are actually in the CVMFS repository, so you don't have to copy them over. You just have to make sure that those libraries are in the path. So it's just a matter of updating the environment path. example, the LD library tab, so that it points to the libraries in the CVMFS repository.
When we think of this, we sort of look at software roughly categorized into code that you write that's your own. And then you have external packages, any number of them, and maybe some special biology. So things that are like that, that are more what we call either shared software, what you want to put into that you have to ask. What do you ask Lincoln to do that? Then you've got your own code, which is presumably smaller and lightweight. Use those two together. So you're not really relying on workstation anymore. You're really using your workstation as the launchpad. Well, code there, you write your code there. What happens after you submit, out there, your job lands on some CPU. That's the basic.
It's because some of the larger software, they sort of assume that they've already been installed in the standard system locations, user bin, and that their libraries are in, say, /lib or wherever. And so when the application tries to request that these libraries get loaded, the OS will just look in the standard system library locations. It won't look in the locations that are under the CVMFS mount. So that way your application will get an error. If you change the LD library path environment variable to point to those other locations in the CVMFS repository, kernel or the OS will actually check there as well, and then they'll find it there and load it from that location.
Library path command is telling your program to look inside into the CVFS directory for your library.
Dynamically loaded libraries.
Library path.
It's in your JavaScript.
Yes. So you just set it in your script, and then whenever that script runs, it'll do it automatically for you. All right, so here the jobs have completed, and if we take a look, we have it's completed and gotten results, and we have timing information. All right, so if you look at the Twiki or your user guide, we actually have a list of software that is currently available in the UC3 CVMFS repository. We have Mathematica, R, Octave. We have Python 2.7 with Scientific Python and Numeric Python installed, and 2 different versions of root. This list will probably change over time, but we'll update the Twiki in this table so that we have the updated versions available.
You put out your registration portal, and I think we kind of fielding that for software. Also, new things in there that we don't actually have. Software that you don't have here, you can put it in that. Check.
Yeah, if you ask us to install R3.
We've sent an email to UC3. Other questions about software? So this is, so what Chandра's covered right here is basically, basic access mechanism to file system. Now the next thing is to do
Yeah.
Okay, then we're going to go to storage.
Or are we going to go over to Mike's? Or
Okay, we got 2
Redmond?
minutes. Okay, so maybe before we, so the last part of this was to scan through these last items. Go through them on your own. So the first one here is storage. So that just describes the storage system where you can log into, UC3 server data, UC3 data, and you should be able to see a directory there. In we have 2 different types of. We sort of organize this in 2 ways. One is that you copy some data that is what we call semi-persistent data. Is some data that you want to keep around for some period of time under user/your CNET ID, and then maybe you want to just write some scratch. You're going to delete. Scratch this, you can put it there, and then we just basically just writing down what our storage policy. So it's not going to get backed up. This is storage. We'll delete files. There are no quotas, so one person can actually use it, and then they will. So if the capacity gets above 80%, we'll start.
Yes. So yes, HDFS isn't POSIX compliant or fully POSIX compliant. There are 2 major issues. One, once you've written a file and closed it, you can't modify it. You can append to it, but you can't change anything that's been written. And the second big issue is you can't do random writes. So you have to write in a sequential order. And some applications, VI, for example, if you edit a large file, will do random writes, and you'll get errors if you try to do that on a file in the HDFS file system. But if you're doing a streaming write, like say a CP, NV, that sort of thing, they should work fine. And depending on what application you're using, they may or may not be okay with just streaming writes and not being able to do random writes. Yes, unfortunately.
But there was at some point an issue with.
Yes. So yes. Mm-hmm.
Oh, the workaround is no longer a workaround.
The general gist is if you when you activate the endpoint, if you copy it to /mount hdfs-nfs, and under that tree, you should be able to use Globes Online to write into the HDFS file system without issues. We have a
So HDFS/NFS is like a different mount point.
yes, exactly.
Okay, but it's right.
Yes, it does a limited amount of reordering of writes, so that Globes Online presents data blocks in a sequential enough order that you can use that with that NFS amount point.
And hopefully one of these days, Globes Online will have a bottleneck.
there is a comment on pages protected.
Yes.
That is the, yeah, you could actually just technically read out of the other one.
Yeah.
Yeah. It's basically the rights that
Code wants to access it from the node, you just use the HDFS.
Yes.
Exactly.
Yes.
But I mean, if it's not clear in that document, just make a note. Okay, so we have Globus Online there. Then we have, there's another section here which is very important, accessing data and software from anywhere. So the software access we've already, well, no, we haven't actually covered the distributed software access. So we covered the case where CBMFS scheduling a job to a resource that has the UC3. We haven't talked about access, except that Lincoln did his example. Access, no matter where your job is. And that's what Parrot and Chirp are for. And, well, Parrot and CBMFS, let's say that. And what Suchandra has done is he's written some here called skeleton, so if you go through this section here, you should be able to get what you need to know to configure your application to use skeleton key. Let's just call it skeleton. The job can run anywhere and
Or anything else actually.
With skeleton.
And I probably asked this question before, but file system,
One directory and everything underneath it.
multiple things at once.
Yes. Yes.
So I could use Parrot on an OSD node somewhere to mount the UC3 and my data on SD Cloud.
Yes, exactly.
And maybe some software directory that I have.
Yeah. So you can use software out of CBMFS, read your data from SPT Cloud, and then write the results into SPT Cloud, and do this from pretty much anywhere in
So
OSU
if I have some
or
software that's medium sized,
wherever.
then we just point to it instead of
Yes.
having it all.
all right, and this is, again, this is probably the most, I would say, ambitious part of the tutorial. Really the hard part, right? So, I would really appreciate it if you do get here to this point, is to go through this and find out what's working here. We haven't put this totally, I mean, this is all, it all works, but the documentation here hasn't been put to have, comments on this. Okay, so go back to the agenda here, and then just to say the last thing here is we talked about the root, there's another one, the octave example that might be. And so now so that's basic, those are really the fundamentals of UC3 at this point. Basic capabilities that we currently have. Now what we're going to do is turn the floor over to Mike, who is going to show use of Swift on UC3 to add another layer of management. In fact, I should say that you can actually do PowerPoint from this one. Is it linked into the agenda? So I think we want to do the PowerPoint for this one because then it gets shared. That one doesn't get shared. All right, so I should say that a lot of the work that's been scheduled onto UC3 has actually been managed by Swift. So this can be potentially. Okay, so Mike, it's all yours.
Okay, hi. So I'm Mike Wild. I'm here at the CI and at Argonne, and I'm the PI and project manager of the Swift project. It's something we've been developing here at Argonne and U Chicago for probably over 10 years now, I guess. Time flies. To cut to the chase, since things are running late, what Swift is a higher level language for orchestrating the execution of your application. Clusters and distributed platforms like UC3, as well as a large set of other resources. So unlike the Condor mechanisms that you've been seeing for it to date, Swift is a little bit higher level. So it lets you basically express the logical way in which you want to run a large number of applications and orchestrate them together. In other words, form a workflow. And it has several things that it does for you. So first of all, it basically makes the parallelism in your program transparent. You don't have to sort of carefully figure out exactly how to wait for a set of jobs to complete and then send their output to the next stage. It does all of that via a programming model called data flow. So while a Swift program kind of looks like a C program, I'm going to try to get to the code real fast. So I'll sort of maybe overview it another minute or two, and then we'll jump right into the code over here. So automated parallelism, automatic distribution. So this is a big thing. So with Swift, you can sort of write the same orchestration of your science code or your engineering code. For example, run it on the campus cluster midway and have that same workflow definition with no changes to the code, overflow work into UC3 or send work to the Cray Beagle or send it out to OSG nodes or Exceed nodes. So benefit number 2 is this transparent distribution of your application code. Benefit number 3 is automated retry failures. So if you're running thousands of applications and there's transient failures due to either your application or infrastructure, Swift will retry those applications on other sites or on the same site on other nodes before it gives up. And you can specify how that retry to do. Okay. So if you load the Swift tutorial, let's see where we are here. If you basically do tutorial Swift, you can get started here. And so what I'll do is sort of get the code up on the screen. You can try the code, and then I'll sort of walk through, little bits of it. Okay. Let's see. So use the tutorial command to say tutorial Swift. Okay, and then you cd to UC.
Oh, it's already one.
The default screen here. Transparency. So the first, I've got 3 examples here to try, and actually, we can actually see what we're going to walk through. The first thing we're going to do is just basically run what we call a bag of tasks. Okay, so that's p00.swift. Excellent, fits on the screen. 00 there at the end. So this is what we're seeing here. Just run just running n copies of the simulation program. So in Swift, the first thing you do is you write application definitions, which basically take a command line invocation of any program you want to run and give it a functional interface. So we're taking this shell line, which is formed in this manner, and giving it the function name simulation within the Swift script. So Swift is kind of a programming language that has some of the attributes of shell, some of the attributes of Perl and Python, and some of the attributes of C. So the syntax is vaguely C-like in the sense that we use curly braces and ifs and selects and switches and things like that. It's shell-like in the sense that we define external commands that we're going to run with command lines. So unlike the rest of the code, which is more programmatic, these are command lines that are literally invoked in that manner, sort of like forming a Condor submit file. And we can pass to that command various data variables from the Swift script, including file variables or scalars like ints and strings. And the language has arrays and structures very much like C. That's a sort of a dynamic feel, much more like Java objects or Python objects, things like that. Garbage collections. So then basically to run, if I have a program, which I'm just calling simulation here, I form it with this command line. Because I'm running this in the UC3 environment, I'm going to actually send my program code as data to the UC3 compute nodes. Okay, so the first argument here is the script that I'm going to send. The functions that start with an at are built-in functions in the language. And this particular function takes a file variable being passed in and places its command, its actual file name on the command line. So throughout the program, I'm going to be referring to files with ordinary variables with this type definition that I've given here. And what I'm basically doing in this program, to cut to the chase at the bottom, is for some number of requested simulations, I'm basically invoking the simulation function. And the for each statement is very much like a for statement, or like a for in Python, for example. For each member of this collection, do this loop body, except the for each does the entire loop body in parallel. So the other thing I don't have to worry about when I'm programming in Swift here is that Swift will do the throttling and so for example, if I want to do 10,000 jobs here, 10,000 instances of my simulation, Swift will conceptually launch all of those in parallel. And the number that will actually run in parallel will be determined by various throttles in the runtime system that control how those jobs are sent to the underlying systems. So you can go ahead and try this program. One thing to note here is that just like many other languages, Swift can pull arguments off of its command line invocation. So when you run the actual Swift script, you can tell the entire script how to behave, various runtime parameters. In this case, we're setting the number of simulations to run and the range of values that each simulation should be constrained to return. Okay. So when you look at what's in this directory, you'll see that see what we have here. So we have the Swift script, and then we have the program that the Swift script is calling. So down here, when I'm defining the simulation script that I'm going to run as simulation.sh. So simulation.sh is sort of like your application here. It's a little mock application that we're, using to, somewhat simulate a real science simulation. Okay. It happens to be a tiny little shell script that generates random numbers with a few different parameters around it. So it's kind of a nice, trivial little hello world kind of example that we can play with all sorts of aspects of writing these kinds of scripts. So you may want to just actually run this by saying Swift and then p00.swift. And I will do that here, and we'll see if we're seeing the same thing. Exactly. Yeah, thank you. So first we'll invoke it without any command line arguments. We'll just say Swift in the script name, and it'll run it right here. So it's just going to run 10 copies of the Swift executable local/op local. Are you not getting the Swift app? Let's see. Somehow it got out of your path. Let's see. Okay. Let's see, which Swift? Is user local Swift 094 is in your path? Okay.
It should be an empty profile, I believe. So it should be
Possible that maybe your path changed from some other. Has everybody else been able to run this? Okay. Okay, I'm sorry, we missed a step here. Did you run, you need to run setup dot. Source, let me do this back here. So you should do this first. Source, setup dot sh. Okay, and it's actually, this is assuming you are a bash user. I didn't write a C shell version of this. So you should see this first with setup. Sorry about that. Yeah. I didn't read my own README here. What setup is doing is actually putting a few config files for Swift in your $home/.swift directory. And there's one file that basically lists the location of where to find applications. In other words, the things that are listed in an APP function. And there's another thing that describes what your cluster is like, okay, in terms of how to run jobs on the cluster. I should mention another benefit of Swift is that as you go from cluster to cluster, the Swift language stays the same, even though you may be using PBS command language on one cluster and Slurm on another and Condor on yet another. Or you may be using cloud resources that don't even have a scheduler and just have some kind of resource provisioner, like Nimbus or OpenStack or things like that.
So is that one of the main benefits?
Dagman. Okay, so good question. So Dagman is a layer on top of Condor. The difference between Swift and Dagman is sort of several-fold, but in general, Dagman is lower level, Swift is higher level. With Dagman, what Dagman lets you do is explicitly specify control dependencies so that when you say when one task finishes, do these tasks, or this task depends on these tasks finishing. And that's all you can say. Dagman alone doesn't automatically transport your data. Dagman alone doesn't give you this system independence. And also, DAGMAN doesn't have the programming constructs that Swift has in terms of being able to express parallel loops and things like that. So when you use DAGMAN for anything of moderate to sophisticated complexity, you have to write some kind of layer around it that generates the DAG. Okay? Okay. With Swift, you basically write your flow as normal functions and loops and control statements like that. And Swift figures out at runtime how to basically create a dynamic DAG that is functionally equivalent to DAGMAN, but is always based on data dependencies. Right? So in other words, Swift is able to make your programs run transparently in parallel because it knows the dependencies between the inputs and outputs of every function you invoke that you specify in Swift.
So let's say I'm running on Fosco. I don't know if job is going to go. I can't write that.
That's actually not the case. I mean, if you're running in a Condor environment, and you manage your
value word, anything that you work from Condor.
So Bosco is a translator.
But it's translating from the Condor language to anything else. And the same if you use your laptop. If you want to go directly, like with Swift, you can go directly to the UC3. If you are in the UC3 environment,
the campus computing cluster Midway. The same Swift script can run on Midway as on UC3 with no changes to the script, just by specifying. Correct. They have it there as a module, so you can, like you bring in other software packages on Midway, you say module load Swift, and then Swift is available. Oh, I should mention that on any system that doesn't have that, Swift is just a tarball. Untar the tarball. If you have Java, it's ready to run. So there's no build involved. It's very easy to install.
I mean, one of the things that we haven't had a good chance to a lot of the capabilities that are coming with Swift, a little bit of overlap with some of the infrastructural capabilities in UC3. Really talked enough, I think, about what's the best way you want to advise people. Right, that on Midway Swift is installed. In UC3, we, our basic mode is that this is basically what you need when you I mean, I just haven't thought through enough depending on where you're logged in.
Well, I can probably address that a little bit better than I can address the differences between Swift and Bosco. So Swift and Bosco have some architectural similarities in the sense that Swift also can, with solely the availability of SSH, can reach from the place where you're running Swift to the place where you want to run your parallel applications and can basically talk to the schedulers on the remote side and move those jobs over. In fact, Swift could even layer on top of Bosco and Condor, because all it depends on is being able to SSH to some system on which it knows how to talk to the scheduler. So it can talk to PBS-like systems, Slurm, SGE, Condor, LSF, and then on any system that is not in its repertoire of schedulers, it can also let the user manually plan Swift agents, and then Swift can just send jobs there. So for example, we talk to Cloud Nodes that way.
So in this case, I think what you're saying is that if I'm sitting on UC3, on UC3 sub, I can get to Midway.
Go the other way around.
Bosco, like, as if I'm switch up. Or I can go around Bosco.
You can go directly to Midway.
Directly, yeah. So there's
Yeah.
this.
So in other words,
So
I
that's what
understand that Bosco would make Midway look like a Condor submit destination, right? So the biggest difference between Bosco, the Bosco infrastructure, and Swift is that in Bosco you talk Condor, in Swift you talk this programming language. So, and the second difference is that it handles dependencies, and it's got a lot of flexibility in how it gets your data to the point of execution and back, that I'm not going to go into today, but it's got its own data transport infrastructure, and it can use other transport infrastructures like GridFTP, SCP. It can actually retrieve data with, HTTP and WebDAV, things like that. So it's basically has a set of drivers to allow it to talk to schedulers and a set of drivers to let it talk to data servers. So the salient differences are, higher level language versus Bosco and Condor, where you maybe have more exact control over what kinds of nodes you go to and things like that. So it's kind of a different scheduling model.
And the other thing, there's a very practical matter here. If you're using Swift on then you arrive at Midway with your at the moment, what we have in UC3, if you are on UC3 sub and you're submitting there, you're actually going into a group account on Midway, which is actually we have a gigantic, and that's one of the things that we need to involve. So I would, I think that one of the things that we need to be able to do is be able to have the job assume its identity, have the submitter and use the RCC allocation. Money when you arrive at it. Important for accounting.
Which would happen if you were using Swift. So for example, let's say you're a campus user and you have access and allocations to Beagle, the Cray system, and to Midway, and maybe to a departmental cluster such as those run by Kim, and UC3, UC3 via your CNET ID. You can sort of pick which one of those is going to be your home base of operation. In other words, where your primary data pools reside and things like that, where you typically do your interactive analysis from, and then you can use the other places as destinations for your jobs, either in a spillover manner or in a direct manner. Like you may run on Midway and do almost all your computation on Beagle, or you may run on Midway and compute on Midway when Midway's free, but also try to get extra cycles out of the entire UC3 infrastructure down through the tier 2 levels and the OSG levels and things like that. Alrighty, so quickly, you may want to just jump to example PO2, program O2, and what I tried to show here is some of the flexibility you get in terms of the data flow. So in this case, we started with this original simple set of simulations. Then in PO1, we showed an example where we do all these simulations and Swift automatically waits for them to finish before running the analysis section. Something you could do with DAGman, but if you're running in sort of a non-Condor place, many users would have to sort of say, okay, I'm going to write my PBS script, and I'm going to have a little loop that says, are all my jobs done? And I'll keep checking with the scheduler to see if my jobs are done. And when my jobs are done, I'll do this. Well, Swift knows when your jobs are done because you declared all your data dependencies in this fairly succinct scripting language. So it knows when this step should run. And furthermore, now in PO2, we make it a little more complicated. We say, well, every simulation is going to be a processing step that's actually going to determine something about the granularity of the simulation, the number of time steps. So that the number of time steps across this ensemble of simulations is determined by running another program. And this program itself may finish in some kind of varying time. So as each of these finishes, Swift is automatically starting the dependent job step for you. If I want to run this from Midway to Beagle and UC3, then Swift could be sending all of these jobs in any level to either machine, so long as your application code behind it runs on those machines. Swift doesn't do anything magic in terms of giving you application code portability. You're still responsible for finding a version of your application that runs on the different resources. But also, it doesn't go into the application and make a given application parallel. What it parallelizes is the workflow ensemble of running many applications at once. So if you look at PO2, you sort of see a kind of a simple program that just looks like function calls, but those function calls are actually implementing this data program. So unlike DAGman, where I have to explicitly say, this task depends on all of these tasks. In Swift, you basically write the output of these simulations to an array, and that array is really an array of files. And those files really just exist in your file system, not in your Swift script memory. So in other words, Swift maps files on the file system to data structures in its program space. In the case of PO2 here, let me put PO2 on the screen here. So I've declared an array of files, and every time I produce a file, I map it to a particular file name in the directory, and then I assign that particular file to this array. So now, from a Swift programming point of view, the output of these simulations is conceptually going into this array. Okay, so this array, in some sense, is, because I've declared it as type file, that means that this array is basically a mapping of essentially file names of where my data really exists on a storage system. Then when I come down to wanting to run my final analysis, I just pass the array name to the analysis program, and Swift is smart enough to know that all of the members of this have to be complete before it can run this. So in other words, write functions, get a DAG is kind of the model here. Write functions and you get an automated dynamic runtime flow graph that coordinates everything. The function analyze is an APP function. So it should be up. Oh, there. Okay. Sorry. So I'm just trying to translate. So these there it is. Are APP functions. Think of them as Swift wrappers around application programs. They're application wrappers. So they take a command line, Okay, so basically what this is telling, what you're declaring here in Swift is that when I invoke the function analyze, I'm really going to invoke the command sh of this script name with these arguments. And standard out is going to go into that file. So it's kind of the connector, the glue code between the Swift world of, transparently parallel functions and the external world of, command line invocations of application programs on cluster nodes. They're generated automatically. So if you actually look in your $home /.globus/scripts, you'll see the Condor submit files that Swift generated for you. You can take a look at here. Show you one.
So
Okay.
then these functions are the wrappers for the
Correct. In the version of Swift we're showing you here, which is kind of the current production version, all communication from between programs and from programs to Swift is via files. Okay. Under DOE funding, we're actually creating what we're starting to call Swift 2.0. The internal name is Swift Turbine or Swift/T, which is a really highly scalable version, taking the same programming model, but letting it run on systems of hundreds of thousands or millions of cores. So it's done under DOE exascale funding. And the two big changes in there are A, that we're allowing library functions, in-memory library functions to be used in addition to APP functions as the leaf functions that Swift can execute. So in that model, Swift could call a library function, or it could call an application program as one of its, atomic leaf functions. And the second big thing is that instead of having such a vast amount of parallelism controlled by a single node invocation of the Swift interpreter, Swift itself has become an MPI program. So it could use, for example, hundreds of nodes to drive hundreds of thousands or millions of nodes. Okay. So we've actually tested that on, up to the, 160,000 core level. And so to give you an example of what we're doing in that project, it's not just to allow calling finer grained functions, but we're trying to call functions that instead of running for like seconds to hours, could run for seconds down to milliseconds. Okay, and in the current Swift interpreter is a Java program. It sort of peaks out at around 500 tasks per second. Okay, so if you had 500 nodes and you were running 1 second tasks, it could pretty much keep those nodes busy. But beyond that, it starts to drop off. So it's great for running multi-minute jobs. It's not so great for running sub-second jobs. Swift-T can run well over 1 million tasks per second from this MPI program. So it's starting to get up there. So now you could keep 100,000 nodes busy with 1/10 of a second, with 100 millisecond, leaf tasks.
So then
They're more than welcome to. They're not our primary audience, but yeah. So I think did you mean to end at 12:30? So I'm happy to stay around and keep going as long as you guys want, but I also don't want to hold you up. Or what conclusion stuff do you want to go through?
Yeah, I just wanted to say a couple words. Just reminding me.
So maybe I can just take any questions and then we can just wrap up. Or so I'm assuming all of these exercises are available to you. You can try them after the session. I'm not sure if anyone actually ran PO2 yet, but you can run PO2. You can try the different scales and sizes. You can actually go to the underlying scripts that are in that directory, which is just analyze.sh and simulation.sh, and just play with those arguments so you see what Swift is translating from and to. And the pointer to the Swift website with the user guide is on the UC3 Jamboree Swift subsection. And there you'll find a user guide and some papers that talk about Swift at a slightly more computer sciencey level, and pointers to applications, other examples and things like that. You can download Swift on your own. You can run it on your your laptops. It runs very readily on Linux and Mac. It runs okay on Windows, although we've seen a couple of window version portability problems. But our window user community is almost non-existent. I don't see any Windows boxes here, so not too worried about that. Any questions about Swift, its intent, what to do with it, what it can do for you? You can actually say, sort of graphically, you can say Swift-TUI, and what you get is what we call the textual user interface. It's actually a crucis-driven graphical thing, so you can sort of tab between 8 different screens that show you different views of the program's progress. So for example, you can see number of jobs run, amount of data moved. You can see jobs in terms of Swift functions and jobs in terms of the underlying scheduler functions. There's a view that lets you actually see the progress in the source code. So you can actually see the source code and you'll see what lines of the source code are running, things like that. We're not real big on graphics, but we're thinking about how to get there. Mm-hmm. Yeah. Mm-hmm. Yeah, we pretty much work full time too. So the Swift team is about 6 or 7 people, depending on how we count them, where they are. We have support line. We don't have the staff that Globus Online has, although I sit right next to the Globus Online support people. The Swift team comes out of the Globus group, and we've got ongoing discussions about bringing Swift into Globus Online, so that Go execute might at some point be